We are now going to look at the consequences of the Poynting vector, power flow, and power associated with conductors. Here we have a battery attached to a resistor. So we know that the voltage across the resistor, I times R, is equal to the applied battery, and it's also equal to the electric field intensity in the resistor times the length of the resistor. So the electric field intensity is the current flowing times the resistance divided by the length of the resistor, and it's in the Z direction. Let's now apply Ampere's circuit law. So for outside the resistor, the magnetic field intensity is I over 2 pi rho in the phi direction. So on the surface of the resistor, the magnetic field intensity is I over 2 pi A in the phi direction. So we have the electric field intensity and the magnetic field intensity on the surface of the resistor. In the Poynting vector, we're going to substitute for the electric field intensity and the magnetic field intensities their values on the surface of the resistor. This results in a magnitude of I squared R over 2 pi AL in the minus rho direction, so it's pointing into the resistor. Minus the integral over the surface of our resistor of the Poynting vector dotted with the outward surface differential will give us the power flowing into the sides of our resistor. The result of that integration is I squared R. So Poynting's vector tells us that the power flowing into the resistor is the power lost in the resistor. Let's now look at what the Poynting vector tells us about power flowing from a source to a load. We will use a coaxial cable to deliver the power from our source to our load. This is a cross-section through the coaxial cable showing the magnetic field intensity lines and the electric field intensity lines. On the inner conductor, the current is flowing in the Z direction, so into the page. You can find the magnetic field intensity lines as we just did using Ampere's circuit law. So inside the coax, the magnetic field intensity is I over 2 pi rho in the phi direction, and A is the radius of the inner conductor, and B is the radius of the outer conductor. We can use Laplace's equation with our two boundary conditions that the potential on the inner conductor is V and the outer conductor is grounded to find the electric potential everywhere inside the coaxial cable. And we can take minus the gradient of that electrical potential to find the electric field intensity inside the coaxial cable. Now let's take our cross product between our electric field intensity and the magnetic field intensity that we just found to get the Poynting vector. So this vector describes the power flowing from our source to our load. We will now integrate the Poynting vector over the cross-sectional surface of the area between the conductors in our coaxial cable. So the differential surface area will be rho d phi, and the outward normal will be in the Z direction. So in the rho direction, we will integrate from A to B, and in the phi direction from 0 to 2 pi. Here are the details of that integration, and we find the result is I times V. So the energy flowing from the source to the load flows in the non-conducting space between the inner and the outer conductors, even in the case of DC. The power is not carried by the electrons flowing in the wires, but by the electric and magnetic fields outside the wires.